In the distant past, deep within the ancient supercontinent known as Pangia, far from the comforting embrace of the ocean, an extraordinary event was unfolding. Our time-traveling extraterrestrial visitors have arrived at a critical juncture in Earth's history, where they witness a transformative moment, the onset of a torrential downpour. This rainfall is not just an ordinary weather pattern. It signifies the beginning of a relentless storm that will last for over 1,000,000 years, forever altering the trajectory of life on Earth. Situated off the western coast of present-day Canada, significant volcanic activity stirs beneath the Earth's crust, setting off a chain reaction that makes this unprecedented rainfall all but inevitable. While the Earth has seen its share of catastrophic events, this particular eruption will lead to conditions that allow for the rise of dinosaurs, a remarkable evolutionary leap that would reshape the biosphere. What makes this event particularly fascinating is that volcanic eruptions of this magnitude are usually linked to mass extinction. Yet, in this case, the eruption that precipitated the rain was unique. It was a paradoxical situation where destruction served as a precursor to creation. Imagine the butterfly effect. If the flapping of a butterfly's wings can cause a tornado hundreds or even thousands of miles away, what might an eruption 100 times larger than a supervolcano trigger in terms of environmental upheaval? Today, we will delve into the story of how an extinction-level event approximately 230 million years ago did not merely end life but instead spurred a surge in biodiversity and accelerated the evolution of dinosaurs. We will explore how Earth's cyclical changes influenced this phenomenon and examine the role of fossil fuel combustion in contributing to climate changes long before the onset of the Industrial Revolution. The conditions before the rain. To understand this monumental event, we first need to grasp the state of Pangia during its reign as the largest landmass on Earth. This supercontinent was unlike anything we know today, dwarfing every modern continent combined. Its sheer size meant that vast areas, especially those located in the center, were distant from coastal climates and the moisture they brought. As a result, Pangia experienced a predominantly arid environment, which in turn favored the evolution of life forms that could thrive with minimal water. Around 300 million years ago, during the Carboniferous period, several key species emerged that continue to have ecological importance today. Among them were dragonflies, millipedes, and spiders. This period also marked a dramatic explosion of diapsids, a diverse group of reptiles that would eventually lead to the ancestors of modern lizards, snakes, and archosaurs. Although the name, archosaurs, may not ring a bell, it encompasses the ancestors of both crocodiles and birds, culminating in the emergence of the dinosaurs we are familiar with. The ancient Earth was a tumultuous place, fraught with dangers from above and below. While Hollywood often dramatizes asteroid impacts, the real threats were often hidden beneath the crust. The geological processes beneath our feet hold the key to understanding what triggered this million-year storm. Understanding the Earth's crust. The Earth's crust is surprisingly thin, almost fragile when considering the scale of the planet. If we were to represent Earth using the entire Lord of the Rings trilogy, the layer that supports all known life would fit onto just a single page. Beneath this thin layer, hot plumes of magma rise from the core, exerting pressure and pushing molten rock against the crust. These massive plumes can breach the surface, resulting in what are known as flood basalt eruptions. These eruptions can last for millions of years, creating immense expanses of basalt rock that dwarf even the largest supervolcanoes. Historically, such flood basalt eruptions have been linked to the most catastrophic extinction events, including the infamous Great Dying, during which ocean temperatures soared to a staggering 40 degrees Celsius. Despite life's remarkable capacity for adaptation, it is estimated that over 99% of all species that have ever existed on this planet are now extinct. While the rapid devastation caused by a colossal asteroid may seem unimaginable, the slower, more insidious effects of volcanic activity can lead to long-term ecological disasters. The evidence of catastrophic eruptions. The evidence of these immense flood basalt eruptions is still visible in various parts of the world today. Regions such as the Siberian Traps in Russia, the Deccan Traps in India, and the Wrangelian Large Igneous Province, which stretches across Canada and Alaska, showcase vast, unmistakable swaths of basalt. These geological formations are not only visually striking but are also more than 100 times larger than typical supervolcanoes. When scientists date these flood basalts, they often find that their eruption timelines correlate with significant mass extinction events. However, there is one particular event that stands apart: the volcanic activity in the Wrangelian province, believed to have initiated the Carnian pluvial episode, a remarkable period characterized by over 1 million years of relentless rainfall that transformed arid landscapes into vibrant ecosystems conducive to the rise of dinosaurs. What set the Wrangelian eruption apart from other volcanic events? The answer lies in its size and the unique conditions it created. While it indeed caused an extinction event, eliminating roughly 30% of marine species, it also catalyzed an overall boost in biodiversity. The extinctions were balanced by the emergence of new species better suited to the wetter conditions, effectively making this a time of reinvention rather than mere extinction. The role of climate change to grasp how this remarkable volcanic eruption could induce such transformative changes in Earth's climate, we must draw parallels to the climate change we are experiencing today, particularly concerning carbon dioxide emissions and the release of methane. Massive volcanic eruptions like this one directly release carbon dioxide trapped in the Earth's mantle, but they can also trigger the release of carbon stored in fossil fuel reservoirs. The introduction of magma at temperatures reaching 1600 C to untouched coal deposits would undoubtedly ignite significant combustion, releasing enormous amounts of particulates and greenhouse gases into the atmosphere. This influx of greenhouse gases would have profound effects, similar to the climate impacts we see today. As these gases trapped solar energy, global temperatures began to rise, leading to a hyperactive water cycle. As solar energy heated the land and oceans, vast amounts of water evaporated, creating a feedback loop that intensified cloud formation. The more greenhouse gases accumulated, the more energy was trapped, which in turn accelerated the water cycle. This extreme version of the geological, carbon, and water cycles created a fertile environment for life. Environmental changes and species adaptation. During the formation of the Wrangelian Large Igneous Province, atmospheric carbon dioxide levels surged, reaching concentrations exceeding 1,000 parts per million, about 2.5 times the levels we experience today. This spike in CO2 contributed to temperature increases of 3–4 degrees Celsius, which supercharged the water cycle, allowing moisture-laden clouds to reach even the most arid regions of Pangia. The planet became warmer and more humid, leading to dramatic shifts in climate. Species adapted to dry conditions found themselves facing multiple stresses as old ecological niches were eradicated and new ones formed. The equilibrium of life was shifting. Moreover, the eruption also released hydrogen sulfide gas, which mixed with oxygen and water to form sulfuric acid, commonly known as acid rain. As this acid rain fell, it acidified both the soils and oceans, further straining the ecosystems and the species that inhabited them. Interestingly, geological records from the Carnian period show a notable increase in amber, a substance produced by trees as a protective mechanism when under stress. This suggests that plant life also faced significant challenges during this tumultuous time. The vast volumes of rainfall led to extensive surface runoff, creating erosive flows across the landscape. This slightly acidic water penetrated fissures in limestone and dolomite rocks, dissolving them over time. Our extraterrestrial observers watched as new cave systems formed, providing unique habitats for life to exploit. Eventually, the runoff reached the seas, transporting eroded minerals and rocks into the ocean, nudging coastal ecosystems into new territories. Marine species faced particularly harsh conditions, as large areas of the ocean became anoxic, meaning they lacked oxygen, and highly acidic, unsuitable for existing ecosystems. Species such as conodonts, ammonoids, crinoids, and green algae experienced alarmingly high extinction rates, while dinoflagellates, essential components of today's ocean plankton, managed to thrive. As the aliens monitored the changing conditions from their ship, they expressed disbelief at the AI's predictions of ongoing miserable weather. Meanwhile, on land, one of the earliest known dinosaurs, Herrerasaurus, roamed the now lush environments of Pangia. This remarkable creature, measuring about 6 meters in length and weighing over 300 kilograms, thrived in the warm, humid jungles of what is now South America. With herbivores and competitors rapidly declining, Herrerasaurus found itself in an ecological windfall. Its habitat expanded dramatically across the continent, leading to a boom time for this dinosaur and its contemporaries. The landscape was rich with resources, and the variety of habitats allowed these creatures to co-evolve in ways that would shape the future of life on Earth. The rise of dinosaurs and the lasting impact across Pangia. The footprints of dinosaurs began to etch their marks into the rock strata. During the 3–4 million years spanning the Carnian pluvial episode, the proportion of dinosaur tracks in the fossil record surged